Hello, papackar. I just wanted to raise a couple of points. I wanted to explain a couple of things that you raised in your comments to my last video about sets and the truth of statements about all the elements in the empty set. Now, the first thing you were talking about was an issue considering the convention, as you called it, that for any x, at least if x is not equal to 0, for any x, the value x to the power of 0 equals 1. You said that's merely a convention. No, it isn't. There's a lot more to it than that, right? I'll show you why. Now, let's say we calculate this value, x times x. What's that? Well, you'll know it as x squared. So that's not that strange, something that we're well aware of. But of course, x is also defined as x to the power of 1. So x to the power of 1 times x to the power of 1 equals x to the power of 2. Coincidence? I think not. But if we take x to the power of 2 and multiply that by x to the power of 1, we get x to the power of 3. And if we take x to the power of 2 and multiply that by x to the power of 2, we get x to the power of 4. Or, to take a completely generic case, x to the power of n times x to the power of m equals x to the power of n plus m. Now, where am I leading with that? Well, take negative powers, for example. X to the power of minus n is equal to 1 divided by x to the power of n. So then, if we multiply x to the power of n times x to the power of minus n, that is equal to x to the power of n divided by x to the power of minus n. But of course, sorry, x to the power of n, of course, here, divided to x to the power of n. Of course, that is equal to 1. But of course, this one, as we already saw up there, is also x to the power of n plus minus n equals n minus n is x to the power of 0. So in order to keep all this consistent, x to the power of 0 has to be equal to 1. Of course, the other thing is, again according to this formula here, x to the power of 0 times x to the power of n equals x to the power of 0 plus n. And again, that has to remain consistent. So x to the power of 0 plus n is obviously the same as x to the power of n, and the only way that this can be equal to x to the power of n is if this one equals 1. So it's not just a mere convention, it is a lot more than just a convention. Now, let's get to your issue with the sets. Let's look at these sets here. Each rectangle you see down there is a set. Now, as you can see, this set here contains 3 2-euro coins, 2-cent coins. That set contains 2-cent coins and a 50-cent coin. Now, let's look at the statement for all x, where x is an element of the set, x is a 2-cent coin. Now, obviously, that is true for this set, and it's false for that set. Okay? What happens if we combine these two sets together? Well, if we take all the elements from this set and take all the elements of that set and put them all together in one set, you'll see that the statement would be false for this set. So what would we see is that the statement about that set and that set being true is contingent on using an AND operator between the content of this set and the content of that set. because this statement was false, true for this set, and it was false for that set, and we used an AND operator, it was also false for the combined set. But now, let's make it a bit more interesting. Now let's look at the case where both the statements are true. So let's remove this coin. Now we're looking at two sets, and in both cases the statement will be true. This one is true, and that one is true. So if we put them all together, again, you'll find that the statement is true for the combined set. Because we can use an AND operator. All the coins in set number 1 were 2-cent coins. All the coins in set number 2 were 2-cent coins. So all the coins in the set that is made up of combining the two sets is also true. All the coins there are also 2-cent coins. That remains true no matter how we distribute the coins among these two sets. This was the original distribution, but it remains true if we do this. All the coins in this set are 2-cent coins. All the coins in that set are 2-cent coins. So if you combine the two, all the coins in the combined set will be 2-cent coins, because it is the truth of this statement and the truth of that statement which determines the truth of the combined statement. And then, of course, we're going to look at a very special case, this one, where all the coins in that set undisputably are 2-cent coins, and that's the empty set. What happens if we combine these two sets together? Well, obviously, all the coins in the combined set are 2-cent coins. And we saw already that the way to work out whether the statement is true for the combined set is by looking at each individual set and ANDing the two together. Well, therefore then, the statement must have been true for both sets, even though one of the sets was empty. See? It has to be true. Otherwise, even common sense will break down, let alone logic.